So next we're going to talk about another asymptotic notation called big omega. So big O is an asymptotic upper bound. This is the intuition, is an asymptotic upper bound. Big omega is going to be an asymptotic lower bound. So you're going to see that their definitions are going to be eerily similar. Likewise, that means that the strategies you would use for proving claims around big O it'll mirror in some ways for big omega. So we're going to let f and g be complexity functions. So we'll write that f is big O, sorry, not big O, big omega of g. Big omega of g if and only if, so just as a reminder. So if and only if. So what this means is that if I say that f is big omega of g, whatever follows after this has to be true. And if this is not true, if f is not big omega of g, then whatever comes after this also has to be false. If and only if there exists constants, c, which is going to be a positive real constant, and n0, which is going to be a positive integer, so that for all n greater or equal to n0, it has to be that f of n is greater than or equal to c times g of n. Does anything in this just sort of stick out to you like a sore thumb about this versus the big O definition? So this is the definition of big omega. So if I say f is big omega of g, it has to satisfy this condition. So this should remind you a lot of the big O notation definition. So our big O definition. So it has two constants the exact same way we had them before. So the game plan has not changed in that regard. So your goal is to find the two constants, c and n0, but the inequality has changed. Do you see? The only thing that's changed here is I changed the less than or equals to a greater than or equal. That's why I'm saying it's an asymptotic lower bound as opposed to an asymptotic upper bound. So this is the definition of big omega. I think it's a good idea we consider an example. So we're going to show that log base 2 of n plus 2 is big omega of log base 2 of n squared. So this one's going to be a little fun because I'm going to use some properties of logarithms. So remember, I usually like to say the game plan so the reader knows what exactly we're up to. And remember, we're going to find the two constants. We're going to have to make sure we come up with an argument that guarantees that it's going to work for these two constants. And then I'm going to invoke the definition of big omega, just like I did for big O, to complete the proof. That's at least one way you can go about this. So we find constants. C, which is a positive real number, and n0, which is going to be a positive integer, such that log base 2 of n plus 2 is less than or equal, no, not less than or equal, right? Remember, that's what the big O one is. Big omega is greater than or equal to c times log base 2 of n squared. N squared is all together, by the way, for the argument for or input for the logarithmic function there. And this has to be true for all n greater or equal to n0. So here we go. So now we've stated what we're going to do, but now we got to pick a constant. So we got to think very carefully about this. So I deliberately picked this example to try to get you thinking a little bit, I wouldn't use the word in reverse, but most certainly something along the lines that I would like to engineer a constant. So sometimes when you're working on these kind of claims, there's a lot of standard techniques, but I thought I would give you a little bit of something that requires us to chew on a little bit. So I have an idea. I got an idea here. If I wanted to make it so that the left-hand side is greater or equal to the right-hand side, what I would like to do is pick the constant such that this looks like a term that looks like a logarithmic term like the one on the left-hand side. So I have log base 2 of n. I would like something that looks like log base 2 of n on this side, because I have plus 2 on this side, so I'd make it a little bit bigger if I need it to be. So here's a suggestion I have. Here's a suggestion. Is we can use a property here to help us. So we're going to use this one called the power rule or power law of logarithms. So here's a suggestion I have for this. So what we're going to do is we're going to use this property. This property says, hey, look, if I had something like this. So if I have log base 2 of n squared like this, or this could be any exponent here, what I can do is I can drag that out front, and it now becomes a multiplicative term. So this is actually equal to 2 times log base 2 of n. So the minute you observe this fact, so this is using the power rule of logarithms or power law. So the minute you observe that, what we really have on this side is c times 2 times log base 2 of n. Do you see a way I can just make it so it looks like log base 2 of n on the right-hand side? Any ideas? Well, yeah, well, let's think about it. So if I have a 2 right here, 2 times what is equal to 1? So what's 2 times what is equal to 1? 2 times what is equal to 1? So I could just make it so it's just log base 2 of n. Well, 1/2. I just take its reciprocal. So 2 times 1/2, these two cancel, you get 1, right? So that's what I'm going to pick as the constant. So I'm going to pick c is equal to 1/2. Then we're going to find n0. Then we find n0 so that for all n greater or equal to n0, log base 2 of n plus 2 is greater or equal to 1/2 times log base 2 of n squared, right? That's what it says. So now let's pull out our observation that we got over there using the power rule of logarithms. So that's what I'm going to say. Observe. So observe by the power rule of logarithms that 1/2 log base 2 of n squared is equal to 1/2 times 2 times log base 2 of n, which is equal to log base 2 of n. So now that I have that information at my disposal, let's do this now. So notice for all n greater or equal to 1, that log base 2 of n plus 2 is greater or equal to log base 2 of n. So choose n0 is equal to 1, right? Because the left-hand side now is, in fact, it's strictly bigger than the right-hand side. So I could just pick n0 to be 1. I must stress that n0 doesn't have to be 1. It could be, the strategies I tend to pick tend to make it so I pick c appropriately, so n0 is pretty easy to pick off. It doesn't always have to be like that. So now that I have c and n0, now I can say therefore, by the definition of big omega, log base 2 of n plus 2 is big omega of log base 2 of n squared. And that completes the proof. So that's my box at the end here. It sort of melted. It's actually Miss Kitty sort of climbed on the box and sort of dented it with her weight. So just as a remark, this actually is an interesting case here because it actually shows you that when you have a logarithmic term like that, the power law or power rule of logarithms here, actually it allows you to pull this down and it ends up just being a multiplicative term. So very often when you have proofs that involve logarithms like that, you'll find that this property tends to be very helpful. So at least especially when it comes to big omega or big O claims, you'll find very often this is the case. So that's big omega, everybody.